Good day, students. We're going to start a little bit today on fire and ice. I think that's kind of a cool title one of my students came up with. I think it was Chloe actually. And the interesting thing about today's lesson is to kind of build on to what we started with the last video where we talked about stoichiometry. We're still doing stoichiometry, but we're adding another dimension to that, such as dealing with gases and whether gases can be compared. And across the top of the board, I've written calculations based on standard temperature and pressure. We call it, for simple, STP. STP states that at any gas at standard temperature and pressure is equal to 22.4 liters of that gas. And so that is an equivalency, just like we've told you earlier that you can have the Avogadro number of any substance is equal to 1 mole, which is equal to its formula mass. And we've got some examples on the board here that we'll look at as well. But let me go and get this set up for you, and then we'll talk a little bit more about what's going on here. I'm going to use phenolphthalein. I'm going to use calcium carbide here. I've actually already got the calcium carbide here. It's in this. I'm going to take a few drops of phenolphthalein, which is an indicator for the presence of the hydroxide ion, which I'm predicting is going to be made in this equation when I put calcium carbide plus water. And as you recall, I've shown you that it's okay to write water as either H2O or HOH, both of which it's the same thing, just a different way of expressing it. Now this is phenolphthalein, and it's in it's got 5% alcohol solution. I don't think you can see it from the screen here. Just going to put a few drops. Okay. Now as you can see, there's no color change there. The color change will only take place after the reaction ensues. So I've already got the container that I'm going to put the calcium carbide on, and I've re-zeroed it. I've used a calculation here where I've kind of worked backwards through the problem, saying, okay, if I wanted to have 1 liter of acetylene or ethine, which is the stock name for acetylene, if I wanted to make that, well, how much calcium carbide would I need? So I hypothetically said, all right, let's just start with a very simple number of 1. Then I incorporate the equivalency on the board, 1 mole of any gas, which we say acetylene is a gas. Granted, we're not at STP, but it'll be close. So that's our equivalency. That's our stoichiometry that you've seen before, comparing moles to moles from our correctly balanced equation here, and then calculating for whatever mass that 1 liter would give. And it was around 2.86. Well, I found a crystal in my container there that's close to that. Let me measure it out and just see exactly what it is. And I've got 2.56. So I'm a little bit less than what I had, but that's all right. We'll go ahead and dump that in the container so you can see what's going to take place. You're going to see some bubbles. You should see a change pretty quickly. That was pretty intense. All right, do you see the the purple color there. Now, you may see a little bit of black or soot on the side of it. You're saying, okay, so what's going on with that? Looks like it's about done its due. So, if you look back to the equation, in ideal circumstances, it would burn completely. But if we look here, that's got soot around the sides of that. So what does that tell us about what is excess and what is a limiting reagent in this equation here? I think you have evidence that would support one of those being an excess and one of them being limiting. I'm not going to tell you what that is. I'm going to let you come up with what you think is the best choice for that and give supporting evidence based on what we saw there. All right, we did see the evolution of heat and light. It was pretty spontaneous there. So that's pretty cool. And so we have two separate reactions there. We took the 2.60, which of course we could change that, change it slightly with 2.56, but the same three steps in this one I thought would be interesting for you to look at from the standpoint that instead of looking at what is produced is what would be required. In this case, you could calculate for how much water was required, and obviously we had excess water than what was necessary to utilize all of the calcium carbide. Because if we go back over and look at it, there's no more bubbles, and there's a lot more water. So our prediction on that one is indeed correct. So I hope this has been entertaining perhaps, but I hope also that you can see that you can incorporate another step in stoichiometry in which we can use standard temperature and pressure, create an equivalency to solve for an unknown. I hope the rest of your day is good. We'll talk to you later.